RFC 6979 Deterministic ECDSA. Welcome to the channel. Please consider subscribing. I produce daily videos covering a wide variety of cloud topics with a focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into RFC 6979, a critical specification that revolutionized how ECDSA signatures are generated by making them deterministic. This might sound like a subtle technical detail, but it's actually one of the most important security improvements in modern cryptographic implementations, particularly for Bitcoin and other cryptocurrencies. RFC 6979, titled Deterministic Usage of the Digital Signature Algorithm and Elliptic Curve Digital Signature Algorithm, was published in August 2013 by Thomas Pornin. Before this standard, ECDSA required a random number generator to create the per-signature secret key value, and this requirement was the source of numerous security vulnerabilities in real-world implementations. Weak random number generators, insufficient entropy, or implementation bugs could lead to predictable key values, and even a single key value reuse would immediately compromise the private key. The genius of RFC 6979 is that it completely eliminates the need for randomness during signature generation by deriving key deterministically from the private key and message being signed. This deterministic approach maintains all the security properties of ECDSA while eliminating an entire class of vulnerabilities. The same private key and message always produce the same key value, which produces the same signature, yet this key value appears completely random to anyone without knowledge of the private key. In this presentation, we will explore every aspect of RFC 6979, from the motivation behind its creation through the detailed algorithm specification, to its implementation in Bitcoin and other systems. We will examine the HMAC-based key derivation process, understand why this approach is both secure and deterministic, see how it integrates with existing ECDSA implementations, and learn about the practical benefits and considerations for using deterministic signatures in production systems. The problem with random key. To understand why RFC 6979 is so important, we need to understand the security vulnerabilities inherent in random key generation for ECDSA signatures. The key value, often called the nonce, though that's somewhat misleading, is a per-signature secret that must be generated fresh for every signature. This key value is used to compute the R component of the signature through elliptic curve point multiplication. The mathematical requirement is simple but unforgiving. K must be different for every signature created with the same private key. If you ever use the same K value to sign two different messages with the same private key, an attacker can solve for your private key using basic algebra. Given two signatures with the same AR value, which indicates the same K was used, but different message hashes, the attacker can compute K equals the difference of the two message hashes, divided by the difference of the two S values. Once they have K, they can trivially compute your private key from either signature. This isn't theoretical. The Sony PlayStation 3 hack is the most famous example. Sony's implementation used a static K value for all signatures, meaning every signature they created used the same K. Security researchers noticed that R was always the same across different signatures, computed K from two signatures, and then extracted Sony's private signing key. This key was used to sign PlayStation 3 software, and its compromise allowed users to run unsigned code on the console, completely breaking Sony's security model. But the problem goes beyond obvious bugs like static K values. Weak random number generators are surprisingly common in computing systems. If your random number generator has insufficient entropy, produces predictable outputs, or has implementation flaws, an attacker might be able to guess or brute force your K values. Even if K values aren't identical, if they're drawn from a limited or biased distribution, various cryptanalytic attacks become possible. The Bitcoin implementation used OpenSUSE's random number generator, which generally works well, but there have been cases where random number generators failed due to insufficient entropy on embedded systems or virtual machines. Another subtle issue is the difficulty of testing random number generation. How do you verify that your random number generator is working correctly? You can test that it produces output, but testing randomness itself is challenging. You can't have test vectors with known outputs because that would defeat the purpose of randomness. This makes it easy for bugs in random number generators to go undetected until they cause security failures in production. The fundamental problem is that ECDSA's security relies on both the long-term private key and the per-signature secret key. You need to protect your private key, which people understand, but you also need to ensure key is generated properly for every single signature, which is easy to get wrong. RFC 6979 solves this by eliminating the randomness requirement entirely, making key a deterministic function of values you already have: the private key and the message hash. RFC 6979 Core Concept. The core insight of RFC 6979 is that we can derive key deterministically from the private key and message hash using a cryptographically strong key derivation function, and this derived key will be secure for ECDSA signatures. The key derivation function must have specific properties. It must be deterministic, meaning the same inputs always produce the same output. It must appear random to anyone without the private key. It must produce different key values for different messages. And it must be infeasible to predict key values or learn anything about the private key from observing key values or signatures. RFC 6979 uses HMAC, the hash-based message authentication code, as the foundation for key generation. HMAC is a well-studied construction that takes a key and a message and produces an authentication tag that can only be computed by someone with the key. By using HMAC with the private key as the key input and the message hash as part of the message input, we create a deterministic function that only someone with the private key can compute, but which produces outputs that appear random to everyone else. The specific algorithm is iterative, building up internal state through repeated HMAC operations until a valid key value is generated. The algorithm maintains two internal values: V, which is 32 bytes of 0x01 for SHA-256, and K, which is 32 bytes of 0x00. These values are updated through a series of HMAC operations that incorporate the private key and message hash. The updated V and K are then used to generate candidate K values, which are tested for validity, meaning they must be in the range from 1 to n-1, where n is the curve order. What makes this secure is the cryptographic properties of HMAC. HMAC with SHA-256 acts as a pseudorandom function. This means its outputs are computationally indistinguishable from truly random values, to anyone who does not have the key. An attacker seeing many signatures cannot predict future K values or learn anything about the private key, even though the K values are deterministically generated. This is analogous to how a stream cipher generates a deterministic key stream that appears random to anyone without the key. The deterministic nature provides several advantages. First, implementations do not need to access a random number generator at all during signing, eliminating that dependency and its associated vulnerabilities. Second, the same inputs always produce the same signature, making testing much easier, as you can have test vectors with known expected outputs. Third, there is no possibility of K value reuse because the same message always produces the same K, and different messages always produce different K values due to HMAC's properties. Fourth, implementations in different languages or on different platforms will produce identical signatures for the same keys and messages, which aids interoperability and testing. HMAC-based key derivation. Let us dive into the details of how HMAC is used in RFC 6979 to derive K values. HMAC itself is defined in RFC 2104 and is constructed from a hash function, in this case SHA-256 for Bitcoin. HMAC takes a key and a message and produces a fixed size output, 32 bytes for HMAC-DRBG. The security of HMAC derives from the underlying hash function and has been extensively analyzed and proven secure under reasonable assumptions about the hash function. The HMAC construction involves two hash operations with different padding of the key. The key is XORed with two different constants, IPAD and OPAD, which are 0x36 and 0x5c repeated to the hash block size. The HMAC computation is HMAC equals the hash of the key XORed with OPAD, concatenated with the hash of the key XORed with IPAD, concatenated with the message. This double hashing construction is what gives HMAC its security properties, making it resistant to length extension attacks and other vulnerabilities that might affect simpler constructions. In RFC 6979, HMAC is used in a specific pattern to derive K. The algorithm uses HMAC-DRBG, which stands for HMAC Deterministic Random Bit Generator, a construction specified in NIST SP890A. HMAC-DRBG is designed to generate pseudorandom bits deterministically from a seed, and RFC 6979 adapts this construction for ECDSA K generation by using the private key and message hash as the seed material. The key derivation starts by initializing two values. V is set to 0x01, repeated 32 times, and K is set to 0x00, repeated 32 times. These initial values ensure that the derivation starts from a known state. The algorithm then performs an update operation that incorporates the private key and message hash into K and B through HMAC operations. Specifically, K is updated using HMAC-SHA-256. The HMAC key is K, and the HMAC message is formed by concatenating B, then 0x00, then the private key, and finally the message hash. Then, B is updated using HMAC-SHA-256 of the new K as the key, with the previous B as the message. This gives us updated K and B values that incorporate the private key and message hash in a cryptographically strong way. The algorithm then performs a second update with similar operations, but using 0x01 instead of 0x00. This further mixes the values and ensures the final state has incorporated all the input data through multiple HMAC operations. After these initialization steps, the algorithm enters a generation loop. It updates V to HMAC-SHA-256 of K as the key, using V as the message. The updated V is then treated as a candidate K value. It checks if this candidate K is within the valid range, from 1 to n-1. If valid, this K is then used for the signature. If not valid, which is extremely rare, the algorithm updates K and B again, and generates a new candidate. This continues until a valid K is found, which typically happens on the first iteration. Step-by-step algorithm. Let's walk through the complete RFC 6979 algorithm step by step, examining what happens at each stage and why. This detailed walkthrough will help you understand both the specification and how to implement it correctly. The inputs to the algorithm are the private key D, which is a 256-bit integer for Bitcoin's SECP-256K1 curve, and the message hash H, which is the 32-byte output of double SHA-256 of the transaction data. Step 1 is initialization of internal state. We create two 32-byte arrays. B is initialized to 32 bytes of 0x01, and K is initialized to 32 bytes of 0x00. These specific values are chosen to start the derivation from a known, fixed state. The initialization ensures that different implementations will produce identical results given the same inputs. Step 2 is the first update operation. We compute K equals HMAC-SHA-256 using the current K as the HMAC key, and the message being V concatenated with 0x00 concatenated with the private key D concatenated with the message hash H. This HMAC operation mixes all the secret and message-specific data into K. The inclusion of both the private key and message hash ensures that K depends on both the long-term secret and the specific message being signed. Step 3 updates V using the new K. We compute V equals HMAC-DRBG using the updated K as the key and the current V as the message. This propagates the information from K into V through another HMAC operation. At this point, both K and V have been updated once and contain cryptographic derivatives of the private key and message hash. Step 4 is the second update operation. We compute K equals HMAC-DRBG using the current K as the key, and the message being V concatenated with 0x01 concatenated with the private key D concatenated with the message hash H. Notice this is almost identical to step 2, but uses 0x01 instead of 0x00. This second update further mixes the data and ensures thorough incorporation of all inputs. The use of different constants, 0x00 and 0x01, in the two updates is a standard technique in cryptographic constructions to ensure different data flows through the same operations. Step 5 updates V again, using the new K. We compute V equals HMAC-DRBG using the updated K as the key, and the current V as the message. At this point, the initialization is complete, and K and V contain the initial internal state that will be used to generate K. Step 6 begins the generation loop. We compute V equals HMAC-SHA-256 using K as the key and V as the message. This gives us a new V that we'll treat as a candidate K value. Since V is 32 bytes and we need a 256-bit integer, we interpret V as a big Endian integer. Step 7 tests the candidate K. We check if this integer is in the valid range, from 1 to n-1, where n is the order of the curve, approximately 2 to the 256. If the candidate K is in this range, we are done, and use this K for the ECDSA signature. If not, we go to Step 8. Step 8 handles invalid candidates, though this almost never happens in practice. We update K to HMAC-SHA-256 using the current K as the key, and V concatenated with 0x00 as the message. Then, we update V to HMAC-SHA-256 using the new K as the key, and the previous V as the message. We then return to Step 6 to generate a new candidate. This loop continues until we get a valid K, which probability theory tells us will happen very quickly, almost always on the first iteration. Security analysis. Understanding why RFC 6979 is secure requires examining both its theoretical properties and practical security considerations. The security of deterministic K generation rests on several pillars: the security of HMAC as a pseudorandom function, the properties of ECDSA itself, and the proper implementation of the algorithm. The primary security property we need is that K values must be unpredictable to anyone without the private key. This is achieved through HMAC's pseudorandom function properties. HMAC-SHA-256 with a secret key produces outputs that are computationally indistinguishable from truly random values to anyone who does not know the key. An attacker observing many signatures can see the R and S values, which are derived from K, but cannot work backward to determine K or predict future K values because of the one-way nature of the elliptic curve operations and hash functions involved. Another crucial property is that different messages must produce different K values when signed with the same private key. This is guaranteed by including the message hash in the HMAC derivation. Since HMAC is collision resistant, different message hashes will produce different K values with overwhelming probability. This ensures that K value reuse, which would compromise the private key, cannot occur unless the exact same message is signed twice, which simply produces the same signature again. The algorithm also ensures that different private keys produce different K values for the same message. The private key is incorporated into the HMAC derivation, so different private keys will result in completely different internal states and therefore different K values. This means that even if two users sign the same message, their K values and signatures will be different. The iterative nature of the algorithm, with its repeated HMAC operations during initialization, ensures thorough mixing of the private key and message hash. The two update operations with different constants ensure that the data flows through multiple independent HMAC computations. This provides defense in depth, even if some weakness were discovered in SHA-256 or HMAC. The multiple iterations and different constants would make exploitation more difficult. A concern that sometimes arises is if deterministic signatures leak information through timing or power analysis. Since the same inputs produce the same K value, the computation time and power consumption are identical when the same message is signed repeatedly. However, this does not leak useful information for several reasons. First, the attacker still cannot determine K from timing information without knowing the private key. Second, any timing variations that might leak information are in the private key operations, not the K generation. And third, proper constant time implementations of ECDSA operations themselves are still required, regardless of how K is generated. The standard has been extensively analyzed by cryptographers since its publication in 2013. No practical attacks have been found, and it is widely regarded as a significant security improvement over random K generation. The algorithm is now used in Bitcoin, Ethereum, and many other cryptocurrency implementations, as well as in various security protocols and applications beyond blockchain. Implementation considerations. Implementing RFC 6979 correctly requires attention to several details beyond just following the algorithm steps. These implementation considerations are crucial for security and interoperability. Let's examine the key aspects that developers need to handle properly. First is the HMAC implementation itself. You must use a correct, well-tested HMAC implementation, preferably from a standard cryptographic library. The HMAC construction involves specific padding and hashing operations that must be done exactly right. Most programming languages have standard crypto libraries that provide HMAC, OpenSSL for C and C++, the HMAC module in Python, the crypto package in Go, and so on. Using these standard implementations is strongly recommended over trying to implement HMAC yourself. Second is proper handling of byte arrays and integer conversions. The private key and message hash need to be converted to byte arrays in the correct format for HMAC operations. For Bitcoin's SECP-256K1, the private key is a 32-byte big endian integer, and the message hash is a 32-byte value from double SHA-256. These must be concatenated with V and the constant bytes in the exact order specified by the algorithm. When extracting K from V, you must interpret the bytes as a big endian integer. Third is the validity check for K. You must verify that the generated K is in the range from 1 to n-1, where n is the order of the curve. For SECP-256K1, n is beginning with 0xFF, ending with 41 in hexadecimal. The generated K must be strictly greater than 0 and strictly less than n in practice, with SHA-256 output being 256 bits and n being slightly less than 2 to the 256. Almost all generated values will be valid on the first try, but the check must still be implemented. Fourth, let's consider constant time implementation. While RFC 6979 itself does not have the same constant time requirements as ECDSA signing operations, it is still good practice to implement it in a way that does not leak timing information. The HMAC operations should take consistent time, regardless of the input values. The validity check for K should also be done in constant time, if possible. These considerations are more about defense in depth than strict requirements, but they are worth implementing in security-critical code. Fifth is testing and validation. Unlike random key generation, deterministic key generation can be tested with test vectors. RFC 6979 includes test vectors for various curves and hash functions. Bitcoin implementations should also test against Bitcoin-specific test vectors. You should verify that your implementation produces exactly the same key values and signatures as reference implementations for the same private keys and messages. This testing is a major advantage of deterministic signatures. You can verify correctness without ambiguity. Sixth, we will discuss the handling of the update loop for invalid key values. While rare, your implementation must handle the case where the first generated key is invalid. The loop must correctly update K and V, and generate new candidates until a valid key is found. Make sure your implementation does not have infinite loop potential, though in practice, finding a valid key within a few iterations is virtually certain. Seventh is integration with existing ECDSA code. RFC 6979 only changes how K is generated. The rest of the ECDSA signing algorithm remains the same. After generating K, you compute R and S using the standard ECDSA formulas. R equals the X coordinate of K times G modulo N, and S equals K inverse times message hash plus R times private key, all modulo N. Your implementation should cleanly separate K generation from the rest of the signing process. Bitcoin integration. Bitcoin's adoption of RFC 6979 for transaction signing was a significant security improvement that happened gradually across the ecosystem. Understanding how Bitcoin uses RFC 6979 provides insight into both the practical application of the standard and Bitcoin's approach to security improvements. Bitcoin originally used OpenSSL's random number generator for key generation in its ECDSA signatures. While OpenSSL's RNG is generally secure, Bitcoin developers recognized that eliminating the dependency on random number generation would reduce the attack surface and improve the reliability of transaction signing. The decision to adopt RFC 6979 was driven by both security considerations and the desire for deterministic, reproducible behavior in Bitcoin's cryptographic operations. The implementation in Bitcoin Core uses the libsec P256K1 library, which is a highly optimized library specifically designed for the sec P256K1 elliptic curve used by Bitcoin. libsec P256K1 implements RFC 6979 as its standard method for key generation. The library was developed by Bitcoin Core developers, including Peter Wool, and has been extensively tested and audited. It includes constant time implementations to prevent side-channel attacks and has been optimized for performance while maintaining security. When a Bitcoin wallet creates a transaction signature, the process now works as follows. The wallet constructs the transaction structure with inputs and outputs, serializes the transaction in the signing format with the appropriate SIASH type, computes the double SHA-256 hash of the serialized transaction to create the message hash, retrieves the private key for the input being signed, and calls the libsec P256K1 signing function, which internally uses RFC 6979 to generate K and then computes the ECDSA signature. The deterministic nature of RFC 6979 provides several benefits for Bitcoin specifically. First, hardware wallets can verify their own signatures. After generating a signature, a hardware wallet can verify it before sending it to the host computer, ensuring the signature is correct. This self-verification wouldn't be practical with random key because you couldn't reproduce the signature for verification. Second, transaction signatures are reproducible for testing. Developers can create test transactions with known expected signatures, making it easier to test wallet implementations and detect bugs. Third, there's no dependency on the quality of random number generators in various environments, which is especially important for embedded systems, mobile devices, and hardware wallets that might have limited entropy sources. The transition to RFC 6979 in the Bitcoin ecosystem happened gradually. Bitcoin Core integrated libsecp 256k1 with RFC 6979 support in version 0.13.0, released in 2016. Hardware wallets like Trezor and Ledger adopted RFC 6979 around the same time or shortly after. Mobile wallets and other implementations followed. Today, essentially all modern Bitcoin implementations use RFC 6979 for signature generation, making it the de facto standard for Bitcoin ECDSA signatures. One interesting aspect of Bitcoin's use of RFC 6979 is the addition of extra entropy in some implementations. While RFC 6979 is deterministic, some wallets add optional randomness to the key generation process for defense in depth. This is done by incorporating additional random data into the HMAC derivation. The standard allows for this through an optional additional data parameter. Adding entropy doesn't compromise the deterministic properties because even with the same additional data, the same signature is produced, but it provides extra protection against potential undiscovered weaknesses in RFC 6979 or implementation bugs. This defense-in-depth approach represents Bitcoin's conservative approach to cryptographic security. Comparison with random key generation. To fully appreciate RFC 6979, it is useful to compare it directly with traditional random key generation, by examining the trade-offs and understanding why the deterministic approach is generally superior for ECDSA implementations, especially in security-critical applications like Bitcoin. Random key generation, as originally specified in the ECDSA standard, requires generating a cryptographically secure random number between 1 and n-1 for each signature. This random number must be unpredictable, uniformly distributed across the range, and must never be reused with the same private key. Generating such random numbers requires access to a cryptographic random number generator, which typically relies on system entropy sources like hardware random number generators, timing variations, or other sources of randomness. The primary advantage of random key generation is that it is explicitly random. Each signature uses a different key value even when signing the same message multiple times, which means the signatures themselves will be different. Some people view this as a security advantage because it means an attacker cannot predict what the next signature will look like. However, this advantage is largely theoretical because the security of ECDSA does not depend on signatures being different across multiple signings of the same message. The disadvantages of generating random key values are numerous and significant. First, there is a dependency on random number generator quality. If the RNG is weak, has insufficient entropy, or has implementation bugs, key values may be predictable or reused, immediately compromising security. Second, there is the difficulty of testing. You cannot have test vectors with expected outputs, because the output is random each time. This makes testing more complex and harder to verify. Third, there is reproducibility. You cannot reproduce a signature for verification or debugging purposes, because random key values mean different signatures each time. RFC 6979 deterministic key generation addresses all these disadvantages while maintaining security. The elimination of RNG dependency means implementations do not need access to entropy sources during signing, only during key generation, which happens much less frequently. The deterministic nature enables comprehensive testing with known test vectors, allowing verification that implementations are correct. The reproducibility allows signatures to be regenerated for verification or debugging, and enables hardware wallets to verify their own signatures before sending them. The security of RFC 6979 is equivalent to or better than random key generation when the RNG is perfect, and significantly better when the RNG has any weaknesses. If your RNG is truly cryptographically secure, then random key and RFC 6979 provide equivalent security levels. However, in the real world, RNGs often have weaknesses, insufficient entropy in certain environments, or implementation bugs. RFC 6979 eliminates these risks entirely, providing consistently strong security across all implementations and environments. One common question is whether deterministic signatures lose any security properties compared to random signatures. The answer is no for ECDSA's core security properties. ECDSA's unforgeability, non-repudiation, and message-binding properties all rely on the attacker not knowing K and not being able to predict it. RFC 6979 ensures K is unpredictable to attackers while making it deterministic for legitimate signers. This is analogous to password hashing. The hash is deterministic, but unpredictable without knowing the password. Some protocols might rely on signature randomness for higher-level properties, beyond basic ECDSA security. However, these are rare and typically do not apply to Bitcoin. For Bitcoin transaction signing, deterministic signatures are strictly better than random signatures in practice. The theoretical advantages of randomness do not materialize in practice, while the practical advantages of determinism, particularly the elimination of RNG vulnerabilities, are substantial. Test vectors and validation. One of the major advantages of RFC 6979 is its ability to use test vectors to verify that implementations are correct. The RFC itself includes numerous test vectors for various curves and hash functions. Let's explore how to use these test vectors and why they are so valuable for validating implementations. A test vector for RFC 6979 consists of several components: the curve parameters, including the curve equation, generator point, and order; the hash function used, such as SHA-256; a sample private key; a sample message or message hash; the expected K value that should be generated; and the expected signature R and S values. By running your implementation with these inputs and comparing the outputs to the expected values, you can verify that your implementation is correct. RFC 6979 Appendix A.2.5 provides test vectors specifically for the SECP-256K1 curve with SHA-256, which is exactly what Bitcoin uses. These test vectors include several different messages signed with the same private key, allowing you to verify that your implementation correctly generates different K values for different messages. The test vectors also demonstrate that the K values are deterministic. Running the same inputs through the algorithm multiple times should always produce exactly the same K and signature. Bitcoin implementations should also test against Bitcoin-specific test vectors. The Bitcoin test suite includes transactions with known private keys, transaction data, and expected signatures. These end-to-end tests verify not just the RFC 6979 implementation but the entire signing process, including transaction serialization, message hash computation, and signature encoding. Testing with Bitcoin-specific vectors ensures that your implementation is compatible with the Bitcoin network and other Bitcoin implementations. When implementing RFC 6979, you should test at multiple levels. First, test the HMAC operations themselves to ensure HMAC-SHA-256 is working correctly. Standard HMAC test vectors are available in RFC 2104 and other sources. Second, test the K generation with RFC 6979 test vectors to verify that your implementation produces the correct K values. Third, test the complete signing process with Bitcoin transaction test vectors to ensure end-to-end correctness. Fourth, test edge cases, like messages that produce invalid K values requiring the update loop, though these are extremely rare in practice. The deterministic nature of RFC 6979 makes testing much more straightforward than random K generation. With random K, you can only test that signatures verify correctly, not that they match expected values. With RFC 6979, you can test that every intermediate value, K, R, and S, matches the expected values exactly. This precise testing capability makes it much easier to catch implementation bugs and ensure correctness. Test vectors also facilitate interoperability testing between different implementations. If two implementations of RFC 6979 for Bitcoin produce different signatures for the same private key and message, one or both implementations have a bug. The ability to compare exact outputs between implementations is invaluable for identifying and fixing interoperability issues. This is particularly important in the Bitcoin ecosystem where different wallet implementations need to produce compatible signatures. Performance characteristics. Understanding the performance characteristics of RFC 6979 helps in evaluating its practical impact on system performance and comparing it to alternatives. While cryptographic correctness is paramount, performance is also important for real-world applications, especially when signing many transactions. The computational cost of RFC 6979K generation consists primarily of HMAC-DRBG operations. The initialization phase requires 4 HMAC operations, 2 to update K and 2 to update V. The generation phase requires at least one additional HMAC operation per iteration. In the typical case where the first generated K is valid, which happens with probability approximately 1-2 to the negative 128 for SEC P256K1, the total is 5 HMAC-SHA-256 operations. Each HMAC-SHA-256 operation involves 2 SHA-256 hash computations. So, we're looking at approximately 10 SHA-256 operations for K generation. On modern hardware, SHA-256 is quite fast, especially with hardware acceleration available on many CPUs. A typical desktop CPU can compute millions of SHA-256 hashes per second. The 10 or so hashes needed for RFC 6979K generation take on the order of tens of microseconds on modern hardware. When comparing this to random K generation, the performance is actually similar, or even slightly better, in many cases. Generating a cryptographically secure random number requires accessing the system's entropy source, which might involve system calls, accessing hardware RNG, or other operations that can be slower than pure computation. The pure computational approach of RFC 6979, using HMAC, is often faster and more consistent than accessing entropy sources, especially on systems with slow hardware RNGs or limited entropy. The performance of RFC 6979 is also more predictable and consistent. Random number generation performance can vary depending on the entropy pool state, system load, and other factors. RFC 6979 takes roughly the same amount of time every time for the same inputs. This consistency is advantageous for performance analysis and capacity planning. In the context of Bitcoin transaction signing, K generation is not the performance bottleneck. The elliptic curve operations for computing R and S dominate the signing time. The point multiplication to compute R from K times G takes significantly longer than the K generation itself. Therefore, RFC 6979 doesn't materially impact transaction signing performance. Hardware wallets, which are performance constrained, can still sign transactions at acceptable speeds with RFC 6979. Some optimizations are possible for RFC 6979 implementations. Hardware acceleration for SHA-256 and HMAC can speed up the operations significantly. Implementations can also optimize the internal state management and byte array operations. However, these optimizations are relatively minor compared to the overall ECDSA signing time. The important point is that RFC 6979 does not add significant performance overhead compared to random K generation while providing substantial security benefits. Additional data parameter. RFC 6979 includes an optional additional data parameter that allows incorporating extra information into the K derivation. This parameter provides flexibility for applications that want to add extra entropy or bind K to additional context beyond the private key and message. Understanding this parameter and its use cases is important for advanced implementations. The additional data parameter, often denoted as a in the specification, is an optional octet string that is incorporated into the HMAC derivation along with the private key and message hash. When present, this additional data is concatenated with the other inputs during the K and B update operations. The same additional data produces the same K, while different additional data produces different K values, allowing controlled variation of signatures. One use case for additional data is adding optional randomness while maintaining determinism. An implementation might generate random bytes and include them as additional data. This makes each signature instance use different K values even for the same message, similar to random K generation, but in a controlled and reproducible way. If you save the additional data along with the signature, you can reproduce the same signature later. This provides a hybrid approach. Deterministic given the additional data, but randomized across different signings. Another use case is binding K to transaction-specific context. For example, a Bitcoin wallet might include the transaction version, lock time, or other transaction metadata as additional data. This ensures that even if the same message hash somehow appeared in different transactions, perhaps due to a collision or construction issue, the K values would still be different because the additional data would be different. This provides defense in depth against potential protocol issues. Hardware wallets sometimes use additional data for user verification. The hardware wallet might display a unique code to the user and incorporate that code as additional data. After signing, the user can verify that the displayed code matches what was used. This provides assurance that the signature corresponds to the specific transaction they approved. This binds the signature to the specific user interaction session. The Bitcoin Core implementation through libsec P256K1 supports the additional data parameter. However, most Bitcoin wallets do not use it, preferring pure RFC 6979 without additional data for maximum simplicity and interoperability. Some advanced implementations or specialized use cases might use additional data for the enhanced features it provides. When implementing support for additional data, you must ensure that the concatenation and HMAC operations are done correctly. The additional data is concatenated after the message hash in the K update operations. Empty additional data, meaning no additional data parameter provided, is treated as a zero-length octet string. Implementations must handle both cases correctly and produce the expected outputs according to test vectors. Multi-signature considerations. RFC 6979 has interesting implications for multi-signature schemes where multiple parties need to collectively create signatures. Understanding how deterministic K generation affects multi-signature protocols helps in designing secure multi-party signing systems. In traditional ECDSA multi-signature schemes, such as those used for Bitcoin multi-sig addresses, each party creates their own signature independently using their own private key. RFC 6979 works perfectly in this scenario because each party's signature is independent. Each party uses their own private key and the shared message to generate their K value and signature. The deterministic nature actually helps because each party can verify their own signature before sending it to others. However, more advanced multi-signature schemes that try to create a single signature representing multiple parties face challenges with ECDSA in general, not specific to RFC 6979. ECDSA does not naturally support signature aggregation the way Schnorr signatures do. Protocols like MASIG for Schnorr signatures allow multiple parties to create a single signature that is indistinguishable from a single party signature, but ECDSA does not have equivalent properties. For threshold signature schemes where K of n parties need to cooperate to create a signature, RFC 6979 can still be used by each party to generate their share of the signature deterministically. However, The overall protocol complexity is driven by the threshold signature scheme itself, not by how K is generated. Each party can use RFC 6979 to derive their share of K based on their share of the private key and the shared message. One consideration for multi-party signing is that if all parties use RFC 6979 with the same inputs, they would generate the same K, which would be problematic for protocols that need different K values from each party. The solution is that each party has a different private key share, so even with RFC 6979, they generate different K values. The deterministic property of RFC 6979 applies per private key, not across different private keys. For applications implementing multi-signature wallets with ECDSA and RFC 6979, the recommended approach is standard Bitcoin multi-sig using P2SH or P2WSH scripts. Each cosigner creates their signature independently using their private key and RFC 6979 for K generation. The signatures are then combined in the script to satisfy the multi-sig spending conditions. This works reliably and securely with RFC 6979. Common implementation mistakes. Despite RFC 6979 being a well-specified standard, implementations can still have bugs if developers do not pay careful attention to the details. Understanding common mistakes helps implementers avoid these pitfalls and verify their implementations are correct. One common mistake is incorrect byte ordering. The private key and message hash must be represented as byte arrays in Big Endian format for the HMAC operations. Some implementations incorrectly use Little Endian or native byte order, which produces completely different results. Similarly, when converting the generated V back to an integer K, it must be interpreted as Big Endian. Byte order errors typically show up immediately when testing against test vectors, which is why comprehensive testing is crucial. Another frequent mistake is incorrect concatenation order in the HMAC messages. The K update operation should concatenate V, then the constant byte, then the private key, then the message hash, in that specific order. Getting this order wrong produces different K values. Again, test vectors will catch this error, but only if you actually run the test vectors against your implementation. Missing or incorrect validity checks for K are another issue. Some implementations forget to check that K is in the valid range from 1 to n-1, or implement the check incorrectly. While it is extremely unlikely to generate an invalid K with SHA-256 and SEC P256K1, the check must still be present for correctness. An implementation that accidentally uses K equal to 0 or K equal to n would create invalid signatures. Incorrect handling of the iteration loop for invalid K values is rare, but it is possible. The loop must correctly update K and V, and generate new candidates if the first K is invalid. Some implementations might have infinite loop bugs, or they might not update the state correctly. Testing with test vectors that specifically include cases requiring multiple iterations, if such test vectors exist, can help catch these bugs. Using the wrong hash function is an easy mistake to make. RFC 6979 supports multiple hash functions, but Bitcoin uses SHA-256 specifically. An implementation that accidentally uses SHA-1, SHA-512, or another hash function will produce completely wrong results. Always verify that you are using the hash function that matches your curve and application requirements. Not using constant time comparisons or operations where appropriate can leak timing information. While RFC 6979 itself does not have as strict constant time requirements as the ECDSA signing operations, it is still good practice to implement it with timing attack resistance in mind. The modular operations and comparisons should use constant time implementations where possible. Integration bugs with the rest of the ECDSA signing code are also possible. RFC 6979 generates K, but then K must be used correctly in the ECDSA signature computation. Bugs in computing RS from K, or in DER encoding the signature, can produce incorrect signatures even if K is generated correctly. End-to-end testing with complete signature test vectors catches these integration issues. RFC 6979 and other cryptocurrencies. Bitcoin wasn't the only cryptocurrency to adopt RFC 6979. Many other blockchain platforms and cryptocurrencies have also implemented deterministic ECDSA signature generation, often directly influenced by Bitcoin's adoption. Looking at how different systems use RFC 6979 provides insight into its broader impact and different implementation approaches. Ethereum uses ECDSA signatures for transaction signing, just like Bitcoin. It also adopted RFC 6979 for K generation. Ethereum uses the SECP256K1 curve, the same as Bitcoin, so the implementation details are very similar. Ethereum's Go Ethereum client uses the same libSECP256K1 library that Bitcoin uses, inheriting the RFC 6979 implementation. This shared cryptographic foundation between Bitcoin and Ethereum simplifies cross-chain tooling and wallet implementations. Litecoin, being a Bitcoin derivative, naturally inherited RFC 6979 through its shared codebase with Bitcoin Core. Litecoin uses the same SECP256K1 curve and the same cryptographic libraries. The adoption of RFC 6979 in Litecoin happened around the same time as Bitcoin, as the codebases share the same cryptographic components. Other cryptocurrencies that use different elliptic curves have also implemented RFC 6979 with their respective curves. The RFC specifies how to apply the algorithm to any elliptic curve, not just SECP256K1. Cryptocurrencies using curves like Curve 2, 5, 5, 1, 9 or P256 can implement RFC 6979 with those curves by using the appropriate curve parameters and order n in the validity checks. Some newer cryptocurrencies have moved to Schnorr signatures or other signature schemes, but for those still using ECDSA, RFC 6979 has become the standard approach. The security benefits and implementation advantages are universal across different blockchain platforms. The deterministic nature is especially valuable for blockchain applications where transactions need to be reproducible and verifiable. Cryptocurrency hardware wallets universally support RFC 6979 across all the cryptocurrencies they support. Ledger and Trezor devices implement RFC 6979 for Bitcoin, Ethereum, and other ECDSA-based cryptocurrencies. This consistent approach simplifies hardware wallet firmware and provides uniform security guarantees across different assets. The widespread adoption of RFC 6979 in the cryptocurrency space has made it the de facto standard for ECDSA implementations in blockchain applications. New cryptocurrencies or blockchain platforms that choose to use ECDSA typically implement RFC 6979 from the start rather than using random K generation. This represents a significant success for the standard and demonstrates the value of deterministic cryptographic operations. Relationship to HMAC-DRBG. RFC 6979 is based on HMAC-DRBG, the HMAC-based deterministic random bit generator specified in NIST SP 80090A. Understanding this relationship helps explain why RFC 6979's construction is secure and how it fits into the broader context of cryptographic random bit generation. HMAC-DRBG is a construction for generating pseudorandom bits from a seed. It maintains internal state consisting of V and K values, just like RFC 6979. The state is updated through HMAC operations, and new random bits are generated by repeatedly applying HMAC to the state. HMAC-DRBG has been extensively analyzed and is approved by NIST for use in cryptographic applications requiring deterministic random bit generation. RFC 6979 adapts HMAC-DRBG for the specific purpose of generating key values for ECDSA signatures. The adaptation involves using the private key and message hash as the seed material for HMAC-DRBG. This ensures that the generated key is deterministic, given the private key and message, yet unpredictable to anyone without the private key. The adaptation is straightforward and preserves the security properties of HMAC-DRBG. One difference between RFC 6979 and general HMAC-DRBG is that RFC 6979 generates exactly 1 K value per message, whereas HMAC-DRBG is designed for generating arbitrary amounts of pseudorandom data. RFC 6979 terminates after generating a valid K, while HMAC-DRBG would continue generating more bits if requested. This specialization to ECDSA key generation simplifies the implementation and makes the security analysis more straightforward. The security of RFC 6979 inherits from HMAC-DRBG's security properties. HMAC-DRBG is proven secure under certain assumptions about HMAC as a pseudorandom function. Specifically, if HMAC behaves as a pseudorandom function, then HMAC-DRBG produces outputs that are computationally indistinguishable from truly random bits. RFC 6979's use of HMAC-DRBG construction means that K values are computationally indistinguishable from randomly chosen values to anyone without the private key. NIST's approval and analysis of HMAC-DRBG lends additional confidence to RFC 6979. While NIST standards are not universally trusted in the cryptographic community due to concerns about potential backdoors, HMAC-DRBG has not been found to have any weaknesses or backdoors. The construction is transparent and based on well-understood HMAC operations. The cryptographic community generally views HMAC-DRBG as a solid construction for deterministic bit generation. Understanding the HMAC-DRBG foundation also helps to understand potential future improvements or variations of RFC 6979. If new insights into HMAC-DRBG construction emerge, or if alternative constructions are developed, they could potentially be adapted for deterministic ECDSA signature generation, in the same way RFC 6979 adapted HMAC-DRBG. The modular design of using a well-defined DRBG construction for K generation is a strength of RFC 6979 approach. Future directions and alternatives. While RFC 6979 has been very successful for ECDSA, it is worth considering future directions in deterministic signature generation and alternative approaches. Understanding the broader landscape helps contextualize RFC 6979's role and potential evolution. For ECDSA specifically, RFC 6979 is likely to remain the standard approach for the foreseeable future. The specification is mature, widely implemented, and has proven secure in practice. There is little motivation to change it for existing ECDSA applications. Bitcoin and other cryptocurrencies that use ECDSA will continue using RFC 6979 as the standard K generation method. However, the broader trend in cryptography is moving away from ECDSA toward other signature schemes. Schnorr signatures, which Bitcoin adopted through Taproot, have several advantages over ECDSA, including simpler mathematics, provable security, and signature aggregation capabilities. Schnorr signatures also benefit from deterministic K generation, and Schnorr signature standards typically specify deterministic K generation similar to RFC 6979 as the default or required approach. ECDSA, another elliptic curve signature scheme, is deterministic by design. ECDSA uses a hash of the private key and message to derive K, similar in spirit to RFC 6979 but integrated into the core ECDSA specification rather than being an optional modification of a random scheme. ECDSA's deterministic approach is one of its design features, and the scheme has been adopted by protocols like SSH and Signal that value deterministic behavior. For post-quantum signature schemes, deterministic signature generation is also desirable. Many post-quantum schemes are being designed with deterministic signatures from the start, learning from the lessons of RFC 6979. Lattice-based signatures, hash-based signatures, and code-based signatures all benefit from deterministic approaches that eliminate dependency on random number generation during signing. One potential future direction for RFC 6979 is incorporating additional hash functions. The current specification supports multiple hash functions including SHA-256, SHA-512, and others. As new hash functions are developed and adopted, RFC 6979 could be extended to support them. However, for Bitcoin specifically, SHA-256 is deeply embedded in the protocol and unlikely to change, so extensions to other hash functions would primarily benefit other applications. Another potential evolution is optimization for specific platforms or use cases. While RFC 6979 is already quite efficient, specialized implementations for hardware wallets, IoT devices, or high-performance signing servers could emerge. These would still follow the RFC 6979 specification but might use optimized implementations of HMAC or SHA-256 for their specific platforms. The success of RFC 6979 has established deterministic signature generation as a best practice. Future signature schemes and cryptographic protocols are likely to incorporate deterministic behavior from the start rather than retrofitting it later. RFC 6979's approach of using cryptographic key derivation based on secret inputs has become a template for how to do deterministic cryptographic operations correctly. Security audits and formal analysis. The security of RFC 6979 has been analyzed through both formal cryptographic analysis and practical security audits of implementations. Understanding this analysis helps establish confidence in the standard and its implementations. From a theoretical cryptographic perspective, the security of RFC 6979 relies on HMAC acting as a pseudorandom function. Formal analysis demonstrates this. If HMAC behaves as a pseudorandom function, which is a standard assumption in cryptographic analysis, then the k-values generated by RFC 6979 are computationally indistinguishable from randomly chosen values to anyone who does not possess the private key. This theoretical foundation provides strong confidence in the approach. The HMAC construction itself has been extensively analyzed since its specification in RFC 2104 in 1997. HMAC has provable security properties. It is a PRF, or pseudorandom function, under reasonable assumptions about the underlying hash function. For SHA-256, which is used in Bitcoin, there are no known attacks that break its cryptographic properties. The combination of HMAC and SHA-256 in HMAC-SHA-256 is considered very secure. Practical security audits have been performed on major implementations of RFC 6979, particularly in Bitcoin-related libraries. The libsecp 256K1 library, which is used by Bitcoin Core, has undergone multiple security audits by professional security firms. These audits examine both the correctness of the RFC 6979 implementation and potential side-channel vulnerabilities. The library has been hardened based on audit findings and is considered one of the most secure implementations available. No practical attacks against RFC 6979 have been discovered since its publication in 2013. While this does not prove absolute security, it is strong evidence that the scheme is sound. The cryptographic community and the substantial financial incentives in cryptocurrency have motivated extensive analysis, yet no flaws have been found. This practical track record combined with theoretical analysis provides high confidence in RFC 6979. Some analysis has focused on potential side-channel attacks against implementations. Side-channel attacks try to learn secrets through indirect information like timing, power consumption, or electromagnetic emissions. While RFC 6979 itself does not introduce new side-channel vulnerabilities compared to random key generation, implementations must still be careful about constant-time operations and other side-channel countermeasures in the HMAC and ECDSA code. Formal verification efforts have also been applied to RFC 6979 implementations. Formal verification uses mathematical proofs to show that code correctly implements a specification. Projects like Project Everest have worked on formally verified implementations of cryptographic primitives, including HMAC and ECDSA, while complete formal verification of RFC 6979 in production systems has not been achieved. Progress in this direction increases confidence in the correctness of implementations. The overall security assessment of RFC 6979 is very positive. It is widely regarded as a significant improvement over random key generation, with equivalent or better security in theory and substantially better security in practice by eliminating RNG vulnerabilities. The standard has stood up to over a decade of scrutiny and practical use in high-value applications like Bitcoin without any security failures. Best practices and recommendations. Based on extensive experience with RFC 6979 in production systems, particularly Bitcoin and other cryptocurrencies, we can identify best practices and recommendations for the implementation and use of deterministic ECDSA signatures. Following these practices helps ensure secure and reliable implementations. First and most important, always use RFC 6979 for ECDSA key generation. Don't use random key generation unless you have a very specific reason to do so. The security benefits of RFC 6979 far outweigh any theoretical advantages of randomness. This is now the overwhelming consensus in the cryptographic community and among Bitcoin developers. Second, use well-tested cryptographic libraries rather than implementing RFC 6979 yourself. For Bitcoin applications, use libsecp256k1, which is the reference implementation. For other languages or platforms, use established libraries that have been audited and tested. If you must implement RFC 6979 yourself, test extensively against the RFC test vectors and Bitcoin test vectors. Third, implement the entire signing process in constant time where possible. This includes the HMAC operations in RFC 6979, the modular arithmetic in ECDSA, and the elliptic curve operations. Constant time implementations prevent timing side channel attacks. Use constant time comparison functions and avoid conditional branches based on secret data. Fourth, test your implementation comprehensively. Run the RFC 6979 test vectors for your curve and hash function. Run Bitcoin transaction signing test vectors if you're implementing Bitcoin wallets. Test edge cases, like messages that produce the maximum or minimum valid key values. Use fuzzing to find unexpected behavior with random inputs. Fifth, consider using the optional additional data parameter for defense in depth. Including extra random data does not compromise the deterministic properties, but provides additional protection against potential undiscovered weaknesses in RFC 6979 or implementation bugs. However, ensure that you handle the additional data correctly and understand that it changes the signatures. Sixth, properly protect your private keys. RFC 6979 eliminates key-related vulnerabilities, but you must still protect the private key itself. Use appropriate key storage, encryption, and access controls. For high-value applications, consider hardware wallets or HSMs that keep private keys in secure hardware. Seventh, understand the deterministic properties and their implications. The same private key and message always produce the same signature. This is usually beneficial, but be aware of it when designing protocols. If you need different signatures for the same message, use the additional data parameter or include a unique nonce in the message itself. 8th, stay informed about cryptographic developments. While RFC 6979 is secure, cryptography evolves. Monitor for any new analysis or potential weaknesses. Subscribe to security mailing lists for the cryptographic libraries you use. Apply security updates promptly when available. 9th, document your implementation choices. If you use RFC 6979 with specific curves, hash functions, or additional data, document these choices clearly. This helps maintainers understand the code and helps users verify compatibility. Clear documentation also aids in security audits. 10th, consider the migration path if you're transitioning from random key to RFC 6979. Existing signatures remain valid regardless of how they were generated. New signatures can use RFC 6979 immediately. There's no interoperability issue because the signature format is identical. Users don't need to do anything. The change is purely internal to the signing implementation. Conclusion: RFC 6979 represents a significant advancement in digital signature generation, transforming ECDSA from a scheme that required careful random number generation into one with deterministic, reproducible behavior while maintaining all security properties. This transformation has had profound practical benefits, particularly in the Bitcoin ecosystem and other cryptocurrency applications. The key insight of RFC 6979 is that deterministic signature generation, when done correctly using cryptographic key derivation, provides equivalent or better security than random generation while eliminating an entire class of vulnerabilities. By deriving K from the private key and message using HMAC-based key derivation, RFC 6979 ensures that K values are unpredictable to attackers yet reproducible by legitimate signers. This achieves the best of both worlds: the security properties needed for ECDSA and the practical benefits of determinism. The adoption of RFC 6979 in Bitcoin through libsec P256K1 has made Bitcoin transaction signing more secure and reliable. Hardware wallets, mobile wallets, and Bitcoin Core all benefit from deterministic signatures. The elimination of dependency on random number generators removes a potential failure point and makes implementations more robust across diverse environments and platforms. The specification itself is well designed and clearly written. The HMAC-DRBG construction provides a solid cryptographic foundation with proven security properties. The step-by-step algorithm is straightforward to implement correctly when following the specification carefully. The inclusion of test vectors makes implementation verification practical and reliable. Looking forward, RFC 6979 will remain important for ECDSA applications, while the broader trend in cryptography is toward signature schemes like Schnorr and ECDSA that incorporate deterministic behavior from the start. The lessons learned from RFC 6979 about the value of deterministic cryptographic operations inform the design of new schemes and protocols. The success of RFC 6979 demonstrates that eliminating unnecessary randomness in cryptographic operations, when done correctly, improves both security and usability. For developers and implementers, the message is clear. Use RFC 6979 for ECDSA signatures. Use well-tested libraries like libsec P256K1. Test thoroughly with test vectors. Implement in constant time, and understand the deterministic properties and their implications for your application. Following these practices will result in secure, reliable ECDSA signature generation. RFC 6979 is a testament to the value of cryptographic standards and the importance of practical security considerations in cryptographic design. By addressing the real-world challenges of random number generation in ECDSA implementations, Thomas Portman created a standard that has made digital signatures more secure in practice for millions of users worldwide. Thank you for your attendance. Please consider subscribing to the channel.